So, yes, I'm David. I work for the CCP4 core team, but mainly my work is as part of the dials collaboration with Diamond Light Source and the Berkeley lab. So, a little bit of history first. Dials was first released, version 1.0, 4 years ago, at the beginning of the CCP4 7.0 series. And since then, we have regularly released minor update versions in a pattern linked to Diamond's run schedule. So every time there's a shutdown at Diamond, we prepare a release so it's ready for the next run. Of course, we also discover bugs as we go along, so we patch and bug fix releases as necessary. But over the past year, we've been spending a lot of time preparing Dials 2. And Dials 2 was released very quietly at first for the brave early adopters at the end of October. And then we explored with friendly users in a sort of shakedown period until at the end of November we had version 2.0.2, which was ready for announcement. So last year you should have seen an announcement go to the bulletin board saying that Dials 2 was ready. Dials 2 is not yet available in CCP4 though. We're now already on Dials 2.1, and that will go out with CCP4 7.1 very soon. And you can see more details about the release history at the GitHub page. So a little reminder about the key features of the Dials package. It's a diffraction integration software. We've got a model for extensible beamline and detector format plugins, so you can adapt dials to unusual beamlines quite easily. We do global multi-experiment modeling with smoothly varying crystal models, which is an innovation in dials. It's a 3D profile fitting program using the same algorithms as XDS. Dials is optimized for photon counting detectors of the sort that you find at synchrotrons like Diamond Light Source, although we are doing much better these days with CCD detectors than we used to. We use parallel execution for computation expensive steps like the spot finding and integration. And one of the most important points is that it's a completely freely available open source project, and we welcome contributions and have accepted third-party contributions to the project too. If you like a bit of coding and you want to get involved, that's the page you need to go to. It's the GitHub address. You can fork the project, make your changes, and submit them back to us in the form of a pull request. So Dials 2 differs from Dials 1 in a few ways. So the major advance, the enhancement that we've been working on, is the extending the scope of the program beyond merely integration to now cover the data reduction step, that is symmetry determination, scaling, and merging. In addition, we have improved many of the multi-crystal workflows that you can do in Dials and ZIA 2. We've also introduced a new spot finding algorithm that improves profile determination and therefore improves integration results. We spent a bit of time speeding up a lot of the steps in Dials. Dials was always intended to be a very fast integration program. I'm afraid we never quite made it there. It's about as quick as the others, if not sometimes slower. But we are now targeting this again as a point to really push on. And lastly, as the project has matured, the team has grown. We found it very important to adopt more modern software engineering practices which help keep the code robust and bug-free. And I will mention this and all of these other points in the next few minutes in this talk. So firstly, the dials.symmetry program, and apologies to those of you who were here yesterday at the Diamond MX user meeting slide. You will notice that there's a very high correlation coefficient between my slides and those that James presented yesterday. These are James's slides. So the implementation in dials.symmetry is very similar to pointless. So we're doing basically correlation coefficients between reflections that are related by symmetry elements of the proposed group. We score these based on the intensity correlations, combine the likelihood scores, and finally re-index reflection. So that's what we know that pointless does. We now do that in dial symmetry. In addition, we're doing the same sort of systematic absence check that pointless does to suggest the space group. And we're limited to the 65 MX space groups at the moment. And we're doing the scoring based on the I over sigma of expected absences, so rather similar to what pointless does again. Dials.scale is the program for correcting symmetry equivalence for the modeled experimental effects. And again, we are learning from standing on the shoulders of giants, I should say. So we have produced a program which is based very much on the model that Aimless uses. It's a physically motivated scaling model. However, there are options within dials.scale. You can choose a different parameterization. So you can choose an array-based parameterization, which is more like what XDS does. But the default is to do modeling like Aimless, and like any good scaling program, it also adjusts the error estimates, does outlier rejection, combines profile and summation integrated intensities appropriately, and produces plenty of reports and nice HTML pages with graphs and so on. One of the nice features of dials.scale, which is a little bit new, is that it can do a rapid rescaling when you add or subtract individual data sets or change image ranges. And this makes it quite useful for if you've got a multi-crystal case and you're trying to optimize the ranges of images or the data sets to include. This makes it quite fast to do that with dials.scale. And one of the nice things that is included is an automated protocol for doing this, doing successive cycles of scaling and filtering using CC half results to decide what should go into the final data set. I've used this myself with 20 data sets. I spent a whole morning trying to optimize the images and data sets to include using Aimless. And I came up with a result that I was quite happy with. I put the data sets into the dials.scale automated pipeline for doing this, and I got a very similar data set in just a few minutes without having to do any work. So that was quite nice. Another symmetry-related program within dials is dials.cosym. This is an extension of the multi-dimensional scaling technique published by Brehm and Diederichs. In that case, it was focused on the resolution of the indexing ambiguity for serial crystallography. So dials.cosym can do that, but it's extended also the algorithm to do the dials symmetry style Lowy group analysis for partial data sets. So the idea is you collect lots of data sets that may have indexing ambiguities, and in fact, you don't really know what the symmetry is. Push it into dials.cosym, and this will sort it all out for you using the multi-dimensional scaling protocol and re-index at the end. And this is very powerful. If you've got multi-crystal data, you could, in principle, process or integrate everything in P1, chuck it into dials.cosym, and assuming the data are good enough and you've got enough overlap, it will result in a consistently indexed data set. That was published 2 years ago in Gilday and Winter. And in addition, with these new tools, the symmetry and scaling tools, we've combined these together into a new pipeline called ZIA2 Multiplex. It's a ZIA2 program because it stands above dials. It's a pipeline using bits of dials. And this is even more automation. So you take integrated data, it will run dials.cosym for you, it will run dials.scale, and then it will do a clustering based on either unit cell or CC half measures. So here the scope is similar to the CCP4 program Blend, but we're using different algorithms. Most notably, it's using correlation coefficients, whereas Blend doesn't. Blend just uses unit cell-based measures. This is automatically run at Diamond. I forget how you get it to automatically run, but Diamond people will be able to tell you that. There's a new spot finding algorithm within dials2. The old algorithm is still selectable, but the new algorithm gives better results in most cases. So what we found is that the previous algorithm would tend to produce spots that were a little bit too tight around the strong pixels. And in fact, this spot here has been split into two. It thinks that this is a spot and this is a spot. So the new algorithm, which is slightly more expensive, does an additional pass through the data and tends to expand the spot shoeboxes to encompass the strong pixels in a better way. It also gives a better background level measure at the spot finding step. So this is produces much better integrated data because you're getting more accurate spot profiles. So although you should never look at a graph of merging R factors versus resolution, here's a graph of merging R factors versus resolution. This is kosher because we're looking at a comparison between two methods. In this case, the new method gives lower R factors across the whole resolution range. And of course, better graph, we get better I over sigma across the whole resolution range as well. So the difference here was just choosing a different spot finding algorithm within the ZIA2 run. All right, other little changes. There's been a lot of tidying up in Dials 2. So if you've used Dials 1, you would be sort of familiar with this kind of, at least if you used it from the command line, you'd be familiar with this sort of process. You have a data block file which contains your experimental model, and a pickle file containing reflection data. And we pass that into a program. This spits out a whole load of files. One issue is that it spits out an experiments JSON file, which is actually a different format to the data block.json. And for the users, you probably don't have to care about that, but for programmers, that was quite annoying because you had to use different code to read each file. Another issue was that we spat out two log files, one of which was a mirror of what you saw on the screen, and another one was enormously long, containing debugging information that nobody ever read. So we've tidied up as the program's grown and become a little more sensible in its middle age. It now does more sensible things. So we have a single format. We can have the EXPT or experiment file. We've got rid of the JSON extension. That's now the same type of file at every stage of the process. What was I going to say about that? Yes, it's the same type of file, which makes it much easier for developers. We've also renamed the output files for the reflections, so a .refl file. And we spit out a much smaller log file, which is friendlier to work with. You can still get the long file if you pass the -v switch to the program. So the new extensions are more descriptive, more useful, less confusing, and they hide the implementation details. And that, in fact, that is useful. So for Dials 2.1, we've changed the format from pickle to message pack, because pickle files are a security risk. I don't know if anyone knew that, but inside a pickle file, you can hide executable code. That's not a good thing for a widely used software project to support. So we're using a safer data storage format for intermediate files. As I said, the debug logs were rarely useful. And we're going to tidy up other things and make things more useful for users. So from the next release, the terminal output will be colored according to severity of warning messages, and the log files will contain more timing information. There's been a lot of tidying up behind the scenes as well. So as ever in a collaborative, large-ish collaborative project, there's always discussion about how to format your code and what the code should look like. And we just got rid of all of that discussion by taking a leaf out of Henry Ford's book, following the maxim, you can have any color you want as long as it's black. And the black software formatter program does that for us. So on every commit, the code is rewritten by black to adhere to a standard format. And that's very useful for external developers also looking at the code. They will see something that is consistent. Flake8 and Clang format also do this. So Flake8 makes sure that the code adheres to Python's internal style guide, and Clang format does similar for C++. Also, every commit is run using a static analysis software based at lgtm.com, which I think that stands for looks good to me. And this is very useful because it discovers issues that could be bugs. And maybe further development would take something that was a bit confusing and turn it into a bug because it wasn't so well written in the first place. So doing this analysis and identifying these things early means that the code is more robust and you don't get as many bugs. So we've been working on this for a couple of years really with this setup, and I'm happy to say that according to LGTM, we're now an A+ Python project. I don't know what these other projects are, but we're right up there at the top, 100,000 lines of Python, and they're all rated very highly. Another issue is Python 2 has retired. It was the end of life of the Python 2 series at the beginning of this year, and Python has been a real stalwart and a very important program for lots of scientific software, but it's moving on and has now retired. And I didn't mean that Python, but this Python, or maybe some of those other Pythons should have retired too, but so following a major effort at Diamond, Dials 2.1 now fully supports Python 3 environments, and from the future version, probably called Dials 3, Python 2 support will gradually be dropped. That's important because many new packages, things for hot topics like machine learning, they're Python 3 only already, so everything is moving forward. Python 2 had a very long life, by the way. It's Python 2.7 was released, I think that's a good 10 years ago, and so it really is time for it to move on from that. So last couple of minutes, one of the things we did in the last week was, as a group, work together to target speed improvements in the code base. And we did this in quite an interesting way, because normally in our project we work as individual developers, getting together for team meetings and then going away and working as individual developers again. We tried a different mode of operation this time. We worked as a group. We did pair programming, so we all sit next to someone whilst they're coding. And that was quite an interesting and rewarding exercise for the team to go through. And it was very productive. Within 1 week, we made a large number of changes, lots of low-level stuff like avoiding additional copies of the data that proved not to be necessary, reducing unnecessary file system operations, and so on. And here's some example results for a particular representative data set. So we see that the dials integrated at the beginning of the week, so on dials 114 branch, we were taking, say, 120 seconds for an HDF5 data set, and we got that down to about 80 seconds by the end of speed week through these changes. For spot finding, we also got an improvement, but of course, we got a new algorithm. So going from dials 114 to the beginning of speed week, we slowed everything down a lot because we got this enhanced spot finding algorithm. And we spent the whole week trying to get back the speed we had lost, and we nearly got there. So just finally, the CCP4 project to develop a graphical interface to dials, DOI, has also changed a lot in the past year. So this is what the old DOI looks like. We've got buttons up the top for the various steps. We've got a lot of information in this panel down here, image viewer here on the right. So cosmetically, a lot has changed in the new version. That status information, it doesn't need to always be there. That's been put away in a tab up here, so you can look at it when you want, not just have it in your face all the time. So there's more room for the image viewer. There's also additional tools now in the image viewer, including masking and the means to check what the spot finding algorithm will do to your data. And all the buttons are now moved here on the left in a way reminiscent to another data processing GUI, not by mistake. And of course, there's now extra buttons for the symmetry and scaling step. So I won't talk much about DOI because Luiso, the author of DOI, is here in the audience, and he has lunchtime bites, I think, both days. A sort of more beginners one today and then more advanced tomorrow. So please come along to the DOI lunchtime bites session if you want to know more about that. And finally, I must acknowledge the whole team. So the Dials East team is head up by Gwyndaf, Graham, and myself. We also work in collaboration with developers at Berkeley Lab who concentrate mainly on the XFEL serial crystallography side, whereas we look at the synchrotron side. And we've had a lot of support and continue to do from scientists at the LMB, Phil, Andrew, Garib, and Harry. And I'm on time, so I'll finish there. Here's a slide just showing all of the various people who house us and fund us. Thank you very much.
How does your new spot finding algorithm deal with split crystals? You know, you
oh, well, it's the spot finding algorithm. Yeah, it still isn't split crystal aware. It's not doing anything special for split crystals, but it is tending now to join the clusters of spots that were separated before in the old algorithm, and now tends to be joined together more because it's giving it. The overall effect is that you get larger shoeboxes and it encompasses more of the strong pixels within the shoebox. So your split crystal you'll end up still with both parts of the split in the box, and the center of gravity of that will be the centroid position for the spot. Not easily. I mean, yes, that would be a nice thing to do, but we don't yet have a way to easily do that. Yeah.
More questions, go to the lunchtime time.